Hi everyone. This represents my return to video after a while. Sorry, I haven't had a chance to make video solutions for the last couple of workshops, but in any event, I did want to do it for this one because I know that we're getting to the topic that everyone finds very difficult, which is using these theorems, forming the right inequalities, proving convergence and divergence. So, just wanted to show you how I would solve some of these problems. A few of these ask you to explain things in your own words. If you're waiting to see what words I would write, I'm going to talk. I'm not going to write out the words because the point is not if you're trying to rework the problems, the point is not for you just to write what I write. The point is for you to comprehend it and try to form the words yourself. Anyway, first one. Let's suppose that f of x is 1 over x cubed plus 2, and we want to use the direct comparison test to prove that the improper integral from 1 to infinity of f of x dx converges. Let's recall what the theorem actually says. The theorem says, in at least in one part, is if 0 is less than or equal to f of x is less than or equal to g of x, and integral from 1 to infinity of g of x converges, then the integral from 1 to infinity of f of x, sorry, there's a dx there, of f of x dx also converges. And just want a little bit of a thinner pen for this. And if you think about it, so why is this? The reason this is that if this is g of x, it looks like that, and let's say that that's f of x, so that's going to be f of x, and this is g of x. It certainly makes sense that if g of x, if we find all the area from 1 to infinity under g of x and it adds up to a finite number, in other words, the integral converges, it certainly makes sense that this red line, there's going to be a smaller amount of area under the red curve, so it certainly makes sense that that would also converge. So the way we prove it is we don't actually compare the integrals themselves, we compare the functions. What we can see is that f of x, the red function, should circle that in red, the red function is actually less than g of x. So anyway, with all that said, we need to find a g of x that is known to converge. So the choice of g of x is going to be 1 over x cubed. Now, why do I choose that? Well, we know that 1 over x cubed is the integrand of something that's called a p integral. We know a p integral is an integral of the form dx over x to the p, like that. And we have certain rules for what values p can have that make this integral converge. In other words, if p, and specifically if p is greater than 1. So we're going to choose g of x is this function. Note that we're not choosing g of x to be the integral, we're choosing g of x to be the function that we integrate. So now, so the question was, of course, without integrating, how do we know it converges? And the answer is because we have this rule about p integrals, and we know that this is a p integral with p equal to 3, and 3 is greater than 1, so we know that the integral is we know that that means that the integral of g of x dx is going to converge. So now what we want to do is form an inequality. This is part B, and it's basically going to be the inequality suggested by this drawing over here. We know as the function we're trying to prove that the integral of it converges is 1 over x cubed plus 2. So let me show you how we form this inequality. Will you agree with me that x cubed plus 2 is greater than or equal to x cubed? In fact, it's going to be greater than x cubed, but will you agree with me that this is true for all x greater than or equal to 1? Assuming you agree with me on that, which you should, will you agree with me that 1 over x cubed plus 2 is less than or equal to 1 over x cubed? In other words, I take the reciprocal of a bigger number, I get a smaller number. So when I take the reciprocal, I switch the direction of the inequality. And of course, once again, this is for values of x that are greater than or equal to 1. So since we're only talking about values that are not only positive, but in fact greater than or equal to 1, would you agree with me that all of this is in fact greater than or equal to 0. So we now have the exact inequality that we see here in the theorem. So this is the inequality that I was looking for. So what we can say is that because, in other words, if I wanted to use this, this was not part of the question, but if I wanted to use this to prove that the integral of that function converges, what I would say is that because 1 over x, well, let me write it the full way as in the theorem, because 0 is less than or equal to 1 over x cubed plus 2 is less than 1 over x cubed on the interval x greater than or equal to 1, and because the integral from 1 to infinity of dx over x cubed converges, therefore the integral from 1 to infinity of dx over x cubed plus 2 converges. That's how we use the theorem. We verified that the hypotheses of the theorem are true. These are the hypotheses. In other words, we formed an inequality and we verified that the right side of the inequality converges. Therefore, this term here must converge. So that's how we used the theorem. That's how we used the theorem. So anyway, this was the inequality that I was looking for. All right. So now let's use a similar technique to show that the integral from 2 to infinity of x to the 9/10 minus 1 diverges. The thing you should be thinking about when you look at this sort of problem is that basically, because we're carrying this function all the way out to infinity, this 1 is not really going to matter at the end. The thing that's going to make the most difference is x to the 9/10. So you can sort of think of it as though 1 over x to the 9/10 minus 1 is basically 1 over x to the 9/10. Now I know what happens. I teach people this technique about saying one function is basically some other function, and they think that that's the whole proof. And then I start seeing, when we turned in tests on paper, I would start seeing test papers where people would say, if I ask somebody to prove that this function diverges, they'd say, oh, it diverges because it's basically x to the 9/10. And the answer is no, that's not a proof. That's the intuition that inspires the proof. So now that we know that basically it's going to be x to the 9/10, at least we sort of know what the target is. We know what inequality we're trying to form. So let's do kind of a similar thing. What we know is that if, once again, if this is g of x and this is f of x, unlike in the first example where I said we know that g of x converges, therefore we can conclude that f of x, that the integral of f of x also converges. Here what I'm going to say is the integral of f of x diverges, and now g of x, which is bigger than that, is going to if I add up all the area under f of x and I still get infinity, it certainly makes sense that if I'm now adding up all the area under g of x, I'd have to get infinity because it's going to be a bigger amount of area. So we're going to do the same sort of thing we did in the previous part, but in reverse. So let me ask you, do you agree? I won't be able to hear your answer. This is a video. Do you agree that x to the 9/10 minus 1 is less than or equal to x to the 9/10 for all x greater than or equal to 2? And the reason I'm starting at 2 is because that's where the integral starts. So hopefully you agree with that statement, that if I take something and subtract 1, that's going to be less than just the thing where I don't subtract 1. Alright, so now we do that same operation again. We're going to take the reciprocal, 1 over x to the 9/10 minus 1, 1 over x to the 9/10, and I'm just going to flip and when I do a reciprocal like that for positive numbers, I flip the inequality, so it becomes that. So we can see is that this function here, 1 over x to the 9/10 minus 1, is greater than 1 over x to the 9/10. And by the way, of course, for x greater than 2, they're both going to be greater than or equal to 0. I know some of you are saying, wait, doesn't the 0 go on the left side of the inequality? It doesn't really matter which way I write the inequality. This inequality is absolutely equivalent to writing this. In other words, I can simply I can simply switch the direction of the alligator and just move everything like that. Okay, so what I now have here is I have this is the integrand of a p integral with p equal to 9/10, which is less than or equal to 1. And we know what the rule is that if I integrate a p, if I have a p integral with p less than or equal to 1, we know that that integral diverges. So what we can say is, so first let me number the steps. So this is the inequality. You have to form the inequality. Then we're going to have to say that we have a p integral that diverges x to the 9/10 diverges, and you have to say why. The answer is because p is equal to 9/10, which is less than or equal to 1. That's the condition for a p integral to diverge. Therefore, now that we have all of the conditions that are in the theorem that would be used to prove divergence, this is the comparison test theorem, direct comparison test theorem. Because we have all of those conditions, we can conclude, 3 dots means therefore, we can conclude that the integral from 2 to infinity of dx over x to the 9/10 minus 1 also diverges. And we put our little end of proof symbol. There we go. Okay. So that's what an answer would look like to part C. Now, let's see. Consider the inequality 0 less than x to the 1/2 plus 1 less than x to the 1/2. So, is this inequality true, and does it show that the integral from 1 to infinity of x to the 1 of dx over x to the 1/2 plus 1 converges? So, first of all, let's call it not part A. So I'm reusing symbols. Let's call it part I. So, is it true? And the answer is yes. It's certainly true that x to the 1/2 plus 1 is greater than or equal to x to the 1/2, and therefore 1 over x to the 1/2 plus 1 is less than or equal to 1 over x to the 1/2. So we've certainly shown that yes, it's true. The inequality is true, but that's not the end of the story. Just showing that one function is less than some other function doesn't show that that doesn't show that the integral of that function converges. So here's the thing. So for 2, does it show convergence? The integral from 1 to infinity of dx over x to the 1/2 diverges, right? Because this is a p integral with p equal to 1/2. And 1/2 is less than or equal to 1, so we know that this integral diverges. So all we've shown really is that the integral from 1 to infinity of dx over x to the 1/2 plus 1 is less than infinity. Or sorry, I shouldn't say it's less than an integral that adds up to infinity. It's less than a divergent integral. That's a better way of saying it. So think about what that means. If I have, let's say, this is 1 over, this is y equals 1 over x to the 1/2, and this is y equals 1 over x to the 1/2 plus 1. So what I know, put a different color. So what I know is that if I add up this, in other words, if I were to integrate this function on the interval from 1 to infinity, I get infinity, right? In other words, this pink area here adds up to infinity. So the question is, what does this yellow area add up to? We know it's less than the pink area, but it could be infinity as well. That's the thing about infinity. It's not a number. Um, if I take twice infinity, that's still infinity. If I take half of infinity, that's still infinity. It's also possible that the area under the purple curve, which is the one we're being asked about, it could add up to a finite number, in which case the integral would converge. We just don't know from this inequality. Saying that, sorry, let me just write it here. So if this diverges, showing that a function is less than a function whose integral diverges doesn't show anything. It just means you don't know. You're going to have to use some sort of other analysis. So that was the point of part D. All right, let's go to part 2. All right, so suppose we want to use the direct comparison test to prove that the integral from 2 to infinity of x cubed minus 1 converges. So why can't we just say, for example, why can't we just write 1 over x cubed minus 1 is less than or equal to 1 over x cubed, and of course that would be greater than or equal to 0. So why can't we just write that? There's a very simple explanation that you all know from previous math courses, which is that you shouldn't write a false statement. So the reason you can't write it is because this inequality is false. Let me show you why. So if x cubed minus 1 is less than or equal to x cubed for all x greater than or equal to 2, once again, that's where the 2 comes from. It's certainly going to be the case that 1 over x cubed minus 1 is greater than or equal to 1 over x cubed once we take the reciprocal and flip the inequality. So here what we have is we have this when we integrate it. By the way, I'm not pointing out that 1 over x cubed is a convergent function. The point is that if I integrate 1 over x cubed, the integral is convergent. So that's what I'm saying here. So that's a convergent integral. And so what we know is that if I integrate this, it's bigger than a convergent integral. So bigger than a convergent integral. So what does that mean? In other words, if this is 1 over x cubed, and this is 1 over x cubed minus 1. So all we know really is that if this adds up to a finite number, so that's going to be finite, what about this? This is going to be bigger, certainly. So is every number that's bigger than a finite number also finite? Well, it could be infinity. So we just don't know, for the same reason as in part D of the last problem. Showing that something is bigger than a convergent integral does not show convergence, for the same reason that showing that something's smaller than a divergent integral does not show divergence or convergence. It just shows nothing. So that's why we can't use it. And like I said, I'm not going to write out the explanation. I'm speaking the explanation. Hopefully, if you want to go through the exercise of writing it out succinctly, you can write it based on the ideas that I'm talking about. Okay, so what we do want to do is try to form a different inequality that will allow us to show a convergence. Now, I know some of you will say, well, couldn't we just use the limit comparison test? And the answer is yeah, we could. But I just want to show that you can do it with the direct comparison test. I want to show you how to set up the inequality in a situation that's a little bit complicated. So here we have, what we're going to do is we're going to show that, oops, do it this way. We're going to show that x cubed minus 1 is greater than or equal to 1/2 x cubed for all x greater than or equal to 2. Now let me tell you what the biggest mistake we saw when grading the workshop was. You cannot start a proof by showing the thing to be proven. Let me just show you what I mean. Let's suppose that I said prove that for a right triangle with sides of lengths A, B, and C, prove that for a right triangle ABC, a squared plus b squared equals c squared. Now there is a proof of this. It's actually a very beautiful geometric proof that you'd all be able to understand. But the point is that the sort of typical error that I think students make when they first start to work with proofs is they start by saying a squared plus b squared equals c squared, and then they take some steps and start manipulating it. They go, oh, well, a squared is equal to c squared minus b squared. I don't know how this would lead to a proof anyway, but that's not the point. The point is here, this is starting with thing to be proven. This is, and I'm going to put it in red, this is the thing that is wrong. You can't do that. That's not a proof. You have to start with something that you know is true and then try to get to the proof. The only alternative to this is something you might have seen in high school geometry class, which is called a proof by contradiction, where we're trying to prove something is false. So we start by assuming the thing is true and then show that it leads to some absurd statement like 1 equals 0 once we carry out all the steps. Not going to go into that. That's for your proofs course. If you go on in math, you'll take a course called Math 300, where you study proof by contradiction in great detail. The point is, in order to prove that something is true, you have to start with something that you know that isn't the thing you're trying to prove. All right, so let's do this. Let's start with the statement that that 1 is less than or equal to 1/2 x cubed for all x greater than or equal to 2. That's a statement that I think we can all get behind. It's certainly the case that if x is equal to 2, then x cubed is 8, and 1/2 of that is 4. So it's certainly the case that 1/2 is going to be less than that. And of course, x cubed just keeps getting bigger and bigger and bigger as x gets larger. So it's never going to get down to as low as 1. So this statement is true. Now let's invert it. That means that -1 is greater than or equal to -1/2 x cubed. In other words, I just multiplied both sides by -1, and of course when I take two positive sides of an inequality and multiply them both by a negative number, I have to flip the inequality. I mean, that sort of makes sense if you think about it. 3 is less than 4, but -3 is greater than -4. There's just an example of how you have to change the direction of the inequality. Okay, so now what I'm going to do is I'm going to add x cubed to both sides. So this is x cubed minus 1 is greater than or equal to x cubed minus 1/2 x cubed. I just added x cubed to both sides of the inequality. And now finally, I'm just going to combine the terms on the right side of the inequality. So I have x cubed minus 1 is greater than or equal to x cubed minus 1/2 x cubed is just 1/2 x cubed. And there we go. That's the statement to be proven. Good. I'm going to put a little end of proof symbol there. We've proven the statement. So I have now proven that x cubed minus 1 is greater than or equal to 1/2 x cubed. Now, I realize where this is going to get confusing. You're going to be like, wait, why did you start with that? How did you know to do it? This is why Chapter 10 is so difficult for people. And all I can do is say that it just takes practice to do it. The reason it's so difficult is you've done a lot of math. If you've gotten up to Calculus 2, you're very good at a situation where I give you a problem. Maybe it's even a word problem and you learn to identify how to set it up, and then you take the steps and you go and you work toward an answer. This requires inspiration. You have to actually think of something out of thin air to do. And I posted the hint that you'd want to start that way on Piazza when somebody asked, but maybe some of you didn't see it or didn't know what to do with it. But this is the thing that makes this so hard, is that in many cases, there's no process that tells you what you have to guess. You have to sort of look at it and say, I think that would work. And that just comes with practice. And frankly, this is really what mathematics is all about. It's not just following instructions. It's pushing the boundaries of what we know by thinking of things that are going to work. And this is where you start learning to do that. So unfortunately, yes, this unit to some extent grades you on whether you can come up with the right inspiration, and that's simply that's what the material is about. Remember, I told you on the first day, this chapter 10 is very hard. This is part of why it is. We're not even in chapter 10 yet. This is a chapter 8 problem, but we're going to be doing a lot of inequalities and a lot of comparisons, and that's why. So that's this is what you have coming down the pike that is going to be difficult. So anyway, that's the inequality proven. Okay. Now, suppose the integral from 2 to infinity of h of x converges. Explain in your own words why integral from 2 to infinity of a times h of x also converges. Well, here's the thing. Suppose that the integral from 2 to infinity of h of x converges. What that means is that it equals a constant. In other words, it equals some finite number. Well, if that's the case, therefore, the integral from 2 to infinity of a h of x dx is equal to, I can use the linearity property. We didn't require you to do this in the problem, but technically what I can do is I can pull that constant out, and we know that this is just equal to that constant that I mentioned. So this is equal to a times a constant. So this is a finite number, and a times a constant is also equal to a finite number. Well, that's what it means for an integral to converge, is that if I integrate, I get a finite number. So we know that if the integral of h of x converges, in other words, adds up to a finite number, then the integral of a times h of x just adds up to a different finite number, and therefore it also converges. All right, so how are we going to use those two in part D to prove that this integral converges? Here's what we're going to do. We know that x cubed minus 1, just a second, it's greater than, we know that x cubed minus 1 is greater than or equal to 1/2 x cubed. How do we know that? We proved it in part A. So 1 over x cubed minus 1 is less than or equal to 1 over 1/2 x cubed, which, by the way, that latter term is equal to 2 over x cubed. So I now have the inequality 1 over x cubed minus 1 is less than or equal to 2 over x cubed, and of course those are both larger than 0 for x greater than or equal to 2. Okay, so this is kind of step 1 in the use of the comparison test. To do step 2, what I need to do is show that this integral the integral of that function converges. The integral of 2 over x cubed from 2 to infinity equals 2 times the integral from 2 to infinity of dx over x cubed, where this is a p integral with p equal to 3, which is greater than 1. So, in other words, this is just 2 times a convergent integral which converges. How do we know that 2 times a convergent integral converges? That was the whole point of part C, as we're saying if we multiply a convergent integral by some arbitrary constant a, it doesn't change whether it converges or diverges. So that means that this converges. So look what we have here. We have an inequality showing that the function we're trying to integrate, we want to integrate this function and show that it converges that its integral converges. We have that it is less than a convergent integral. So we can conclude that therefore the integral from 2 to infinity of dx over x cubed minus 1 converges. So look at what we did, how we used the two parts above. We used parts B and part C to prove the statement in part D. We used part B, this inequality, to do part 1 of the theorem, to form this inequality here, showing that the integrand was less than something that we felt we could show converged. We then used part C to do step 2. In other words, to show why, when we integrate this, we get a convergent integral. We did that because it's basically a p integral multiplied by a constant. So we now have proven the theorem, and that's the proof of convergence of this integral. And this is a pretty, I would say, sort of clean, plain vanilla demonstration of the type of inequalities that we're going to be forming over chapter 10. So this is something that you should make sure you get pretty good at. We're going to be doing a lot of this. Okay.